All right, so moving right along from the theorem that we just looked at about like adding and multiplying when you're when you're doing modulo m. If you use that alternate definition of A congruent to B mod m, that when you reduce modulo something, so like the remainder when after division by m is the same for those two numbers. If you use that definition and apply it to that other theorem, you can kind of rewrite that theorem into this form. Okay, so this is a corollary to that theorem. And it says that if you take a plus b, if you take two numbers, a plus b, and reduce it modulo m, that's equivalent to taking the a and the b individually and reducing them modulo m and then adding those. But then you have to take that result and reduce that modulo m as well. Similarly, if you take a times b and take the product modulo m, like reduce it mod m, then if you take a and b individually and reduce them mod m, and take that product, and then take the result of that and reduce that mod m, it's going to be equal. So I'm going to show you a couple of examples of this. So example 1 here, let's take a equals 37, b equals 108, and then m equals 10. And we're going to do addition. So 37 plus 108 is equal to 145. Now, if we reduce each of these numbers modulo 10, okay, reduce mod 10. 37 mod 10 is going to be 7, right, because it's 30 plus 7, and 30 is a multiple of 10, so that's just 7. 108 reduced mod 10 is going to be 8, and 7 plus 8, let's see, this would say 145 mod 10. That's going to be 5, right? Because it's 140 plus 5. Now 7 plus 8 isn't actually equal to 5, right? 7 plus 8, well, this is actually equal to 15. But if you take 15 and reduce that mod 10, 5 equals 5. Okay, so we started with this, right? We started with 37 plus 108 equals 145. If you reduce all these numbers mod 10 and add them together and then take that and reduce that mod 10, it's the same as taking the sum and reducing the sum mod 10. So 5 equals 5 in that case. Let's do another example. Let's do another example with multiplication. Okay, so let's take, for this one, we'll do a equals 17, b equals 8, and again, let's do, let's do m equals 5 this time. So we're going to reduce mod 5 this time. So let's do it with multiplication. 17 times 8 is equal to, I just wrote it down. What's 17 times 8? Oh no, here's my calculator. I'll get it back here real quick. It's 136. 136. So now we're going to reduce modulo 5. What's 17 mod 5? Well, it's 15 plus 2, right? So reduced modulo 5, 17 is going to give us 2. What is 8 reduced modulo 5? 8 mod 5 is 3, right? So it's 3. So on the left we have 2 times 3. 36 modulo 5, what's that going to be? Well, 36 is just one more than a multiple of 5, right? It's 135 plus 1. So this is going to be, when reduced mod 5, that's going to give us 1. Well, 2 times 3 is 6, right? That's not 1. So again, it's like, well, it's not immediately the same, right? But if you reduce 6 mod 5, then it's 1. And again, 1 equals 1. So this is a pretty important theorem because this theorem establishes that if you take the idea of addition and multiplication and you reduce everything modulo some specified number, then addition and multiplication are still like well defined in that world where everything is reduced modulo 5 or everything's reduced modulo 12 or whatever you wanted, or modulo 2. It essentially says, hey, everything is still nice and consistent when you reduce it all modulo some specified number. So this is a pretty important theorem that's going to establish something called modular arithmetic, which we'll get to in the next video.